what we want to do next is our next kind of big topic is 2D solutions. And in 2D solutions, what we're going to do is, so far we've done everything in 1D, including our extended surfaces. Remember, extended surfaces are a 1D solution because we're making the assumption that the temperature profile in the non-primary direction is not important, right? It's uniform, basically. So now with this separation of variables in 2D problems, we can no longer make that assumption. Right? Let's say we go through our BO number calculation and it's 0.2 or 0.5 or something. Now we got to do something like this, right? This is a more difficult solution. I mean, it's not hard to do, it just is more work. But there's different techniques that we're going to go through to solve these. So the separation of variables idea is probably best communicated through an example because there's like 5 or 6 steps that we're going to have to go through. So let's just go into this particular example, and then I'll talk through the steps as we go, and we can understand it that way. So this example, a few things first. We have a thin plate, right? So this plate is of thickness B. B is relatively small compared to W and H. And then we have these 4 boundary conditions. On the left-hand side, we have a temperature equals 0, which is a curious temperature. But you'll see, I think, why in a second. We also have a temperature in the y direction of TH. And then we have adiabatic boundaries on the others. So you might actually think of this as, OK, let's say I have, this is a quadrant in a 4-quadrant system, and those are symmetry boundaries or something like that. OK, but this is the setup. If you wanted to prove that this B direction is not important, you could also do a BO number calculation, looking at the resistance to conduction in the Z direction compared to the X and Y, and just prove to yourself that that's small. But I'll just tell you for this problem, let's make the assumption that it is negligible. OK, separation of variables. What we're going to do, start just like always with our control volume. So let's draw some differential control volume. And we have to think about what now this is going to look like. So before we had control volume, say top to bottom or left to right, all the way across the domain. But now we're modeling in two dimensions. So this differential control volume needs to be differential in both x and in y. Right, so it's a differentially small in both directions where we're modeling the temperature profile. What do we have then for heat flows? Well, we're going to have in x, we're going to have a q dot at x. And y, we're going to have q dot and y. And we also have heat leaving. So we have heat leaving at q dot x plus dx and q dot y plus dy, where dx and dy are just the height and width, right? For this problem, let's assume that we don't have generation, it's steady state. So the only thing we're worrying about is just heat flow due to conduction. OK, so let's write out the energy balance here. Again, remember we have in plus generated equals out plus stored. And we are saying generated is nothing and stored is nothing, so we just have in equals out. So in equals out is going to be q dot x plus q dot y, and out is going to be q dot x plus dx plus q dot y plus dy. All right, that's our very simple energy balance. We can now do the same thing we've established the steps before. We're doing all the same steps. We're just adding now this second dimension to it. So what do we need to do? Let's expand out x plus dx, and let's expand out y plus dy. That's going to look like this. Q dot x plus q dot y is equal to q dot x plus q dot x. Oops, let me be careful, right? So now we have 2 variables, or two independent variables. So this is no longer an ODE, right? It's now a partial. So it's the partial operator, q dot x partial x, plus, times dx. The differential length, and then plus q dot y, what did I write? Plus q dot y plus differential q dot y differential y times dy. Hopefully I got all that. All right, cancel stuff out. So q dot x goes away, q dot y goes away, and we're left with, let me just write it down here. We're left with differential q x, differential x times dx, plus differential q dot y, differential y, dy equals 0. Okay, nothing really surprising so far, except now we have, be careful and make sure you understand this. We have a differential operator, right? That's an operator that we're writing, and then we have a differential width, which is the dx and dy. So just kind of make sure you understand that. We can't cancel out, at this stage, we can't cancel out dx and dy because those are different things, right? They're not the same. So those have to tag along for the moment. So now we need to come up with expressions, our rate equations for q dot, again, right? Same thing. So let's plug in Fourier's law, but now it's going to be in x and in y. And there's a little bit of carefulness that we have to show there. So q dot x is equal to minus k times the cross-sectional area available for heat flow. So cross-sectional area available for heat flow in x is going to be dy, right? dy times b. So so we have k times b times dy times our differential operator of t with respect to x. So this is Fourier's law in the x direction. Right? For the y direction, it's going to be similar. Q dot y is equal to minus k times b times dx. Right? That's the area available for heat flow in the y direction times differential of t with respect to y. Does that make sense to everybody? Right? The areas are really important. If you don't do the areas right, the problem's going to be wrong. So make sure you get those. You're careful when we do that. So plug that in. Let's see. We end up with this differential with respect to x of minus k b dy dt dx times dx plus differential with respect to y minus k b dx differential with respect to y times dy is equal to 0. Okay. So now we have conductivity is a constant, b, which is the thickness, that's a constant. What else? dy does not depend at all on dx, right? So dy can actually come out to the front, where dx also doesn't depend on dy at all, so dx can come out to the front. And if we do that, then we have dx times dy, and then in this term we have dx times dy, and those can cancel out. And then we end up with our really simple equation, which is d squared t dx squared, or plus d squared t dy squared equals 0. The simplified version. So this you might recognize from other classes. This is called Laplace's equation. Right? Another way of writing this would be like del squared t. Right, this is a diffusion problem. So this is the diffusion differential equation. Okay, so everybody see, we went through this process. We have a control volume. We're careful about the areas. We then can cancel some out, some of the dx's out, and we end up with a nice symmetric governing equation. So now we can use this. But before we move on, let's maybe identify the equations for the boundary conditions. So let's write over here our boundary conditions. So boundary condition 1. Boundary condition 1 is going to be at x equals 0. So at t at x equals 0 is equal to 0. Boundary condition 2, right? These are in no particular order. Let's stick with the x direction. So boundary condition 2 is going to be at x equals whatever that is, w. So at x equals w, we have dt dx at x equals w equals 0. Being careful to remember that it's still a partial operator, because this entire equation needs to be true for the entire temperature solution at the boundary conditions. Okay, so boundary condition 3. At y equals 0, we have adiabatic, so it's the same thing as 2, but for y. So that would be t dy at y equals 0 is equal to 0. And then at 4, we have t at y equals h is equal to t sub h. Four boundary conditions are ODE, and now we should be good to keep moving.